Okay, so we have come to mixture problems. So I'm going to do this a little bit differently in this class. There are normally a couple of different kinds of mixture problems. And in the past, what I've done when I've taught beginning algebra is just to cover them all here in chapter 2. But based on a suggestion from a colleague, what I'm going to do is just cover some of those problems in this chapter and then save the rest for when we get to chapter 4, where you will learn what you'll likely find to be an easier way to do them. Okay, so there is a certain thing that all of these problems have in common right now. And maybe the best time to explain what they all have in common is not until we get to chapter 4. All right. All right, so first example, this is an example of a percent mixture problem. We want to know how many cubic centimeters of a 25% antibiotic solution should be added to 10 cubic centimeters of a 60% antibiotic solution in order to get a 30% antibiotic solution. So what I suggest you do in all of these problems is to make a chart like the one you see here. Well, let's start with how we label the rows. So the rows are labeled with the ingredients that are being mixed together, and the bottom row represents the mixture. So we're combining a 25% solution with a 60% solution to get a 30% solution. And then the columns are labeled with the amount of each solution times the strength, which is in a percent mixture problem given by the percentage. And that is going to give you the amount of pure whatever, in this case, antibiotic. Okay, so I'm going to switch over to the tablet, and I think you'll maybe have a better understanding of what we're doing once I fill in one of these rows. So first of all, I definitely recommend Mitchell's Commandments for these problems. Look at what they're asking for. In this case, they're asking for how many cubic centimeters of a 25% solution. So I'm going to be a little lazy about this. I'm just going to underline that and then say that equals X. Okay. Okay. So again, to give you a better idea of what we're doing, let's go to the 60% solution, because we know everything there is to know about the 60% solution. We know there are 10 cc's of it. We know the strength is 60%, which I'm going to write as 0.60. And then notice across the top, it says number of cc's times the strength equals the amount of antibiotic. That multiplication sign and also that equal sign both carry down throughout the chart. Okay. So for example, we know that if we have 10 cc's of a 60% antibiotic solution, that means that the amount of pure antibiotic in that solution is 6 cc's, because it's 10 times 0.6. So if you try to picture that, picture it in a little, I don't know, beaker or glass or whatever. Okay, and imagine it's filled up to here. It's saying that about 60% of that is pure antibiotic. Those of you that are going to be nurses, for example, may have to do problems like this when you are doing your job. Okay, so now let's try to fill in the other rows. Let's go to the 25% solution. How many cc's of the 25% solution is there? Well, we don't know, and that's why we're calling it X. But we do know that the strength of the 25% solution is 0.25. So while I can't say exactly how many cc's of antibiotic are in the 25% solution, I can write it in terms of X. It would be X times 0.25 So I'm going to fill in this box with 0.25x. All right, we are almost to the point where we have an equation. So here's how I'm going to finish it off. We want a 30% solution. So the strength of that is going to be 0.30. How many cc's will be in that 30% solution? Well, the 30% solution is a mixture of 10 cc's of one solution and x cc's of another solution. So that's going to give us a total of x plus 10. And how much pure antibiotic is in the 30% solution? Well, there's 6 cc's in one solution. There's 0.25x cc's in the other solution. So that gives us a total of 0.25x plus 6. And voila, here you have the equation that we're going to solve. 0.30 times x plus 10 equals 0.25x plus 6. All right, so now I'm going to go to the next page to solve that equation. So it was 0.30 times x plus 10 equals 0.25x plus 6. So I'll distribute the 0.3. That gives us 0.30x plus 3, right, equals 0.25x plus 6. All right, so now we need the x's on one side. Let's put them on the left side. .05x plus 3 equals 6. Subtract 3 from both sides. That gives us 0.05x equals 3. And if I divide both sides by 0.05, I end up with x equals 3 divided by 0.05, which is 60. All right, so we should write that in a complete sentence. It would say something like you need 60 cc's of the 25% solution. And I'll just point out that that answer makes sense. If you look back at the original problem, we're combining a 25% solution with a 60% solution and getting a 30% solution. 30% is much closer to 25% than to 60%. So it makes sense that there would be a lot more of the 25% solution. All right, next example. All right, I'm going to do this one, and then I would like you to try the next one because the next one is pretty similar to this one. This one says, how much pure acid should be mixed with 2 gallons of a 40% acid solution in order to get a 70% acid solution? So the first step is I'm going to define my variable, how much pure acid, we'll call that x. So now let's fill in the row that we know everything about. We know everything about the 40% solution. We know there are 2 gallons and the strength is 40%. So 2 times 0.4 is 0.8. Okay. And now let's talk about the pure acid. So what makes this problem just a little different from the last one is that you might find, okay, so number of gallons of pure acid is X. You might find yourself getting stuck when you go to fill in the strength for the pure acid row. Well, pure acid means pure acid, right? It means there's nothing else in that solution. So the strength of acid in the pure acid would be 100%, which I'm going to write as 1.00. Okay, so just notice pure acid means 100%. Oops, 100% acid. Oops. All right. So that means the amount of acid will also be x. X times 1 equals x. So just like in the last problem, the amount of mixture will be given by adding these two together. So that's going to give me x plus 2. The strength is supposed to be 70%. And the amount of acid from the last column will be x plus 0.8. All right. So I think I will go ahead and write that equation on the next page. It's going to say 0.7 times x plus 2. Oh, darn it. I guess I'm writing it here. I forgot to skip a page. 0.7 times x plus 2 equals x plus 0.8. Distribute the 0.7. That's going to give us 0.7x plus 0.7 times 2 is 1.4 equals x plus 0.8. Okay, so again, you can put the x's on either the left side or the right side. This time I'm going to put them on the right side. The only reason I'm doing that is so I don't get a negative coefficient in front of my x. Not that that would really be a big deal. Okay, so that's going to leave me with 1.4 equals, now be careful here, x minus 0.7x, remember your invisible 1 there. 1 minus 0.7 is 0.3. And finally, well, not finally, this is the second to last step, we have to subtract 0.8 on both sides, squeezing that in. So that's going to give me 0.6 equals 0.3 times x, and dividing both sides by 0.3, we get x equals 2 gallons of pure acid. As far as I'm concerned, that's close enough to a complete sentence. All right. Okay, last example, and I definitely want you to try this one because, again, I think it's very similar to this one that we just did. This one is asking how much water should be added to 30 gallons of a solution that is 70% antifreeze in order to get a mixture that is 60% antifreeze. Okay, so please pause the video and try that one. All right, let's see how you did. We know everything there is to know about the 70% solution. We know there's 30 gallons of it. We know the strength is 0.7. 30 times 0.7 comes out to 21. So in that 70% solution, there would be 21 gallons of pure antifreeze. How much water? Hopefully you wrote down that that's what we're going to call X. Okay, so what did you come up with for the strength of the water? In other words, what percentage of water is pure antifreeze? Well, hopefully, I don't know about you, but I like my water to be 0% antifreeze. Okay. Which means the amount of antifreeze in the water is going to be 0 gallons. Okay. The number of gallons in the mixture will be X plus 30. The strength of the mixture is supposed to be 60%. And the number of gallons of pure antifreeze in the mixture will be 0 plus 21, which is 21. So our equation is going to be 0.6 times X plus 30. 0.6 times X plus 30 equals 21. All right, distributing the 0.6. We get 0.6x plus 0.6 times 30 is 18. Subtracting 18 from both sides, we get 0.6x equals 3. And finally, dividing both sides by 0.6, we get x equals 3 divided by 0.6, which is 5. So you would need 5 gallons of water. All right. So I think that takes us to the last example. The last example is a little bit different. These were all percent mixture problems. This last example is what's called a value mixture problem. So the example I have looks like this. The owner of a local chocolate shop wants to develop a new trail mix. How many pounds of chocolate-covered peanuts worth $5 a pound should be mixed with 10 pounds of granola bites worth $2 a pound to get a mixture that is worth $3 a pound? All right, so I've got this all written out on the tablet, so let's go over there one last time. All right, so again, this is called a value mixture problem. And I think you can see why it's called that. All right, so the idea behind a value mixture problem, let's look at the granola bites because we know everything there is to know about granola bites. We know there are 10 pounds of them, and we know the unit cost is $2 a pound. So what you can do with that information is if you've got 10 pounds of something that's worth $2 a pound, then you know the total value of that thing, which would be $20. Okay. If you went to the store and asked for 10 pounds of granola bites, it would cost you $20. Okay. All right. So other than that, it's going to be kind of similar to what we were doing in the percent mixture problems. The question is how many pounds of chocolate covered peanuts, so we'll call that X, so that'll go here. The unit cost of the chocolate covered peanuts is $5 a pound, which means the total cost in terms of X will be 5X. All right, so now the number of pounds in the mixture will be X plus 10. The unit cost of the mixture is supposed to be $3. And the total cost of the mixture in dollars will be 5X plus 20. So this is our equation. 3 times X plus 10 equals 5X plus 20. All right, so let's solve that equation. We will start by distributing the 3. 3 times X is 3X. 3 times 10 is 30. And now we'll get all our X's on one side. You know what? I'll stick with the left side this time. Just be careful because 3X minus 5X is negative 2X. If you make only one mistake with your signs, it is likely that your value of X will come out to be a negative number. And if you write your answer as a complete sentence, hopefully you'll catch that. If you do get a negative answer, don't just ignore the negative sign, right? That's sometimes what students do. No, if the answer comes out negative, that means there's something wrong. All right, and now I'm subtracting 30 from both sides. That's going to give me negative 2X equals negative 10. Divide both sides by negative 2. Okay, and now this looks okay. -10 divided by -2 is 5. The question was, how many pounds of chocolate covered peanuts? We would need 5 pounds. Okay, so the only other thing I want to say about these mixture problems in particular is I know they are a little on the difficult side. So if you have trouble with them, believe me that you're not going to be the only one. All right, just remember all the resources you have out there. You have my office hours, you have tutoring, you have the help buttons in the online homework. There's lots and lots of ways to get help. And I'm happy to help you. Just ask me for it. And other than that, that's it. That's going to do it for section 2.6. We'll see you next time.